So
Yeah. So,
no.
2x.
If when we differentiated x squared, we had dx over dt. When I differentiate x here, I cannot have 1, correct? So it must be dx over dt equals,
Where did 4 come
1 second, I'll go back. So when I square 2 times sine, I have to square 2 to get 4, and I have to square sine to get sine squared. I didn't distribute. I raised 2 sine to the second power. So I got 4 and sine squared. Now let's do this second part one more time. So 2x dx over dt, 8 sine to 2 minus 1 times the inner function prime times the further inner function prime. Pi over 2x is pi over 2 times the inner function prime, which is dx over dt. On the other side, too, w times dw over dt. Is this okay? Do we agree? Do we disagree? We're not sure. Any questions?
So
Yes, please.
when we get the x squared line, it breaks out into 2x minus dx over dt.
Because this is a function,
Yeah.
this is basically a function to the second power, prime. 2 times the function prime. So I have 2 times the function prime. Better? Is this one?
I understood that. I just didn't know because then you differentiate x, but it's also just dx over dt.
Yes.
Yeah.
So yes. So when I differentiate the function, I get the function prime. When I differentiate pi over 2 times the function prime, I get pi over 2 times the function prime. Better?
Yeah.
Good. Sure. Anything else? Other questions? Everything okay? Okay. So let's try to clean it up a little bit. And here's what I'm going to do. 2 and 2. No, not this 2. Just this 2. 2 with 8, and I get a 4. So it's 4 pi. So I'm going to try to clean it up a little bit. So 2x dx over dt plus 4 pi, 4 pi, sine pi x over 2, cosine pi x over 2, dx over dt equals 2w dw over dt. Since we are after dw over dt, I can simplify everything again by 2. So I have dw over dt. This is x dx over dt. And this is 2 pi, because I divided everything by 2. 2 pi sine pi x over 2 cosine pi x over 2 dx over dt. You're not surprised that I ran out of room. So x dx over dt plus. I simplify by 2. I get 2 pi. I get sine, I get cosine, and then dx over dt divided by w because I divided by 2. At this point, I have x equals, x was 1/3. I have y equals 1. And I have dx over dt, which is the square root of 10. Only now I can plug in all those numbers. So dx over dt is the square root of 10. This is the square root of 10. X is 1/3. 2 pi is 2 pi. And now sine. When x is 1/3, 1/3 times pi over 2 is pi over 6. So this becomes 1/2. This is pi over 2 times 1/3, so it's still pi over 6. So this becomes the square root of 3/2. Now I'm going to show it in a nicer way so it's clear. So dw over dt is 1/3 the square root of 10 plus 2 pi times 1/2 times the square root of 3/2 times the square root of 10 over 2. Sorry, careful. I put 2 instead of w. No, it's not 2. It's w. And no one said anything on this one. I caught my own mistake, finally. Okay, so everything was okay. I simplified by 2, but it's w here, not 2. And I have to determine w. So I go back to the previous equation. Which equation? This one. And take the square root from both sides to determine w. Because I don't have it here. I need to determine w. Ready? I don't have it yet. Okay. So I'm going to write the original equation one more time. So this is x squared plus 4 sine squared pi x over 2 equals w squared. I will take the square root. You cannot simplify this. So w is the square root of x, which is 1/3 squared, 1/9, plus 4. Sine of 1/3 times pi over 2 is pi over 6. Sine pi over 6 is 1/2. 1/2 squared is 1/4. And that will replace the w in the denominator. By what? The square root of 1/9 plus 1. And now we're ready to plug everything in the graphing calculator. So this was my page 8. This was 9. And this is 10. Ready? All this to determine dw over dt. Okay, so let's do that. Careful. I would rather put parentheses in the numerator and put the square root of 10 outside. But that's fine. Let's do it the way it is. So the square root of 10, I don't like not having parentheses, but I'm going to swallow hard this time, divided by 3 plus. I'll simplify the 2 pi. So I only have pi the square root of 30 over 2. So pi the square root of 30 divided by 2. Am I done there? Yes. Pi the square root of 30 divided by 2. Yes. I close the parenthesis and I divide by the square root. And the denominator is, I will put in parentheses 1/9. I'm almost sure it doesn't need to, but I can't. It's a habit. Okay, so 9.16. 9.16, and now we need the measurement unit. Per, yes. Did you get 9.16? Anyone? Perfect. Did we get the idea? Do we feel a little bit better? I'm sure you're going to come up with some questions from WebAssign. I'm pretty sure when you get to this. Is that good enough for now? Yes? Okay. So we already talked about differentials and linear approximations, but we did not talk about linear approximations. So 3.10, differentials. And linear approximations. I would like to go back to differentials for a minute to refresh our memory what those differentials represent. And also, I would like us to approximate different function values using differentials. Okay. I'm going to go to the next page. So what we looked at last time was something like this. We had a function, f of x, and we said that if this is p and this is x, then this is f of x. And if this is q, and this is x plus a little bit, written any way you like. And this is q, and this is f of x plus dx. We found that this is the exact difference called delta y, uppercase delta, delta y, the exact change. If I have a minor error in x, this is the error in the y, in the function, right? In the y values. And this is f of x plus dx minus f of x. Agreed so far? Okay, then we said, well, can we estimate this somehow? Yes, we can. By creating a right triangle and determining this. And what was that? It was the estimate of delta y. How did we call it? dy indeed. So dy is the differential of y, which represents the estimate of delta y. But we know that q and p are very close. So q and p are somewhere here, very close. So therefore, the difference between this, which is delta y, and this in my drawing, which is dy, here it looks to be huge, it's almost double. But no, q is very close here, so therefore dy and delta y will be very close to each other. That's why dy is an estimate, a good estimate of the exact change. And the next step we did last time was we replaced this by f of x plus dx minus f of x, because that's what it equals to. F of x plus dx minus f of x is this distance. And then we said it's approximately, and we will never confuse this to f prime. This is not f prime. This is f prime of x times dx. And what we did next, we moved f of x to the other side, and we came up with this result, which is a very important result. And now I would like to use this before we look at linear approximation. I like to use it in more problems. We looked at the problem with the disk. There was an error in the radius, and we wanted to determine the error triggered by the error in the radius, the error in the area. But now I would like to look at something else. So see how powerful this result is. And I'll let you choose. So here are some of the problems that I would like you to choose from. Use a linear approximation. No, I want to use differentials. to estimate the given number. This. No one can do this by hand. No one can estimate this no matter what you say and what you do. We will be able to estimate it very easily. This maybe you can. It's not a big deal to raise to a fourth power. This one is kind of tough. This one, tangent 44 degrees. No one knows how to estimate tangent 44 degrees. You can say, yeah, it's close to 1. Yeah, maybe, but how close? I agree, because tangent 45 is 1, but how will you estimate tangent 44? Okay? And anything else. So please choose. There are 6 problems to choose from. Anything you'd like. We want 24. Very good. So this result is so powerful that will allow us to estimate anything we want, number one. Number two is as important as the definition of the derivative, the formal definition f prime of x being the limit as h approaches 0 from the difference quotient, very powerful. It's as important as the definition of continuity at the point, extremely important result. Okay, so keeping that in mind, you don't have to memorize it, right? If you remember that the delta y is approximately dy, this will follow in a blink, just 2 lines, right? Okay. So we want to estimate number 24, which is e raised to, I think it's negative 0.015. I am going to copy the result right here. F of x plus dx is approximately f of x plus f prime of x dx. And you can say, what's this? What are you trying to do? Okay, so here's what I need in order to be able to use the result. I need you to tell me the function involved. I need you to tell me what x is. I need you to tell me what dx is. And of course, once I have a function, the function, I need to find f prime. What's all this? Okay, that's exactly what I mean. I need the function. I need x. I need dx. A function is right there. And I need f prime of x. If I have these 4 pieces, all I have to do is just plug them in. Don't forget, the question is this. Can anyone identify the function for us?
Yeah.
Of course. Can anyone identify x for us? Careful. Careful with x. Say it again.
Negative 0.015. Zero.
Exactly. The closest number to this that is a decent number. You can't go to 1 or negative 1. It's too far. So you will have to say x is 0. Okay, now how much is dx? If x is 0, what could dx be? I only need f prime, and we're done. Right? So now please dictate. This is what I'm looking for. So it's e to negative 0.015, approximately. Approximately what? E to x, where x is 0, 1, plus f prime of 0. Good. Times dx. I will never believe it if you say, oh, I knew that this is going to happen. 1 minus 0.015. I will never believe you. So this is 8590. not in a million years, you would have come up with e raised to negative 0.00, negative 0.015 as being 0.98. Agreed? So let's go to e raised to, in parentheses, negative 0.015 and 1 minus 0.015. Are you happy with this approximation? 3 digits. Very good. Would you have ever thought to be able to raise e to negative 0.015 by hand? It didn't do anything. We didn't use the calculator. We used the calculator at the end to check, to show you the difference between the two numbers. But here we didn't do any calculator work. We didn't do anything. We just looked at this number. We identified 4 quantities, basically 3, and the 4th one comes from the first one, so 3 quantities. And we used the definition in which delta x is approximately dx. And we just plugged in some numbers and we got 0.997.
So why then did we use 0 for x?
Very good. Because I need an x that is very easy to work with, but I can go, remember, dx has to be tiny. So what number is the closest to negative 0.015? It's only 0.
So it just needs to be sufficiently close then. But
In this case, because this is such a tiny number, then only 0 is close to it.
And we chose it because it's specifically because it's easy to work with.
Exactly. And not too far.
Right.
Yes. Yes. See how powerful you are now? You can raise e to negative 0. No one can do this by hand. There is no way. There is absolutely no way. Okay, let's choose another, because I think there might be a little bit of confusion with that 0. So let's, which one?
25.
25. What is 25? Okay, 25 is the cube root of 1001. Good, very good pick. So the cube root of 1001. I write my powerful result. F of x plus dx is approximately f of x plus f prime of x dx. You have to write this several times. You have to remember where it's coming from. I don't want you to memorize it, but I want you to use it. So I need to determine 4 quantities, basically 3. I need you to come up with a function. I need you to come up with x, dx, and then eventually f prime of x. Yes, of course. And what is the derivative then? Remember, this is x to 1/3. 1/3 x to negative 2/3, which is 1 over the cube root of x squared. So this is 1 over 3, the cube root of x squared. Okay, then I need x and dx. Now this will become even clearer, I hope. In this case, it's much easier to identify. Of course. And then what can dx be? It has to be tiny. In comparison to 1000, it's tiny. Yes. That's it. Just plug them in and tell me what to write. Remember, this is that. So then the cube root of 1001 is approximately, what will I write?
Cube root of 1000.
Of course. Excellent. Plus,
Prime of 1000.
yes, 1 over 3, the cube root of 1000 squared times. That's it. How much is the cube root of 1000? 10. How much is the cube root of 1,000, but then squared? So this is 3001 over 300. That's it. Let's do that together. Let's check. So we had the cube root of 1001 . The cube root is 1 divided by 3. And then 3001 divided by 300. Impressive, isn't it? Okay, so you will have a problem like this on the next test and the final exam. Do we need another, or we are okay with it? Yes, of course. I'll let you choose anything you want. Which one? The tangent 44?
Which one you got?
So we did 25 and we did 24. No, I just, I don't know. I'll take care of that. I don't know. It's up to you. 28 it is. We did the cube root. The square root is...
How about 27?
Okay, let's do the tangent. Let's do the tangent. That's how they did it without calculators. Here they use calculus. Okay, so 27. We want to approximate tangent 44. And we know that we have f of x plus dx is approximately f of x plus f prime of x dx. What I need to identify is the function x dx and f prime. Function, please. Of course. X, please. Right. dx.
45 degrees. Well, it should not.
Very good.
Wait, it's 45.
Yes, but this is 45, right?
Yeah, yeah.
So then this is -1, correct. Thank you. What about f prime? Good. So indeed, 45, because we know everything about 45 and dx is small. You can say, why don't you use 90? Well, again, first of all, it's undefined. But you can say, why don't you use 0? Because then delta x would be 44. That's huge. But if I use 45, I know everything about tangent 45, and I will use delta x to be -1 degree. Now, be very careful. We cannot use degrees outside of a trig function in calculus. So here will be okay, here will be okay, but this will not be okay. This is -1 degree, and it's not inside a trig function. So we cannot use degrees. If I use in tangent pi over 4 or 45 degrees, it doesn't matter. Tangent has only one answer. But here, no degrees. Oh, it's double E-S. No degrees. This has to be radians. Because it's outside of a trig function, and it makes a huge difference. Okay, so this is, remember, 180 degrees is pi. 1 degree will be pi over 180. So this is -pi over 180. And this will be dx. One more time, inside a trig function, it doesn't matter if you put in radians or degrees. The answer of the trig function does not depend on degrees or radians that you plug in inside a trig function. But if it's a number in degrees outside of the trig function, you cannot keep it in degrees. Very good. Ready? Okay. So remember, this is what we are trying to do. This is our tangent 44. Approximately what? Tangent 45. Let's write it for everyone to see first, and then we'll plug in the numbers. Plus secant squared 45 times negative pi over 180 in parentheses. And this is 1. Secant 45 is 1 over the square root of 2, right? It's cosine, 1 over cosine. Secant 45 degrees is 1 over cosine 45 degrees, which is 1 over the square root of 2 over 2, which is 2 over the square root of 2, but you have to rationalize. So when you rationalize, you get the square root of 2. But the square root of 2 squared will be 2. With minus, of course. So this is basically reducing to negative 1 minus pi over 90. Or 90 minus pi over 90. This is tangent of 44 degrees. We're going to plug it in to double check. Ready? So make sure your calculator is in degree mode, just for this situation. So I'm going to write tangent 44, and then in parentheses 90 minus pi, close the parenthesis, and divide by 90. Are you happy with the approximation? You had no idea that you can come up with a very good approximation of tangent 44. You had no idea. Would you agree? Would you have come up with 9.65? I don't think so. Any questions on this? Any questions? Questions? Okay, let's talk about last topic, I promise. After this, I stop. Linear approximations. So we are able to estimate or approximate pretty much everything. Looking at the powerful formula that f of x plus dx is approximately f of x plus f prime of x dx. Now this is a similar topic, but also very interesting, and you will see what happens. We can approximate a function, any function, using a linear function. Near a point, of course. Okay. So let's take a look at this function. This is f of x. Yes, our second or third best friend, p. And of course, I'm going to say that p has coordinates a, f of a, of course. And yes, it has to have connections to calculus, of course. I'm going to draw the tangent line at this point. I'm going to ask you what is the slope of this tangent line, and of course everyone will instantaneously say, thank you very much. Good. And then I'm going to ask you to tell me how to write the equation of the tangent. Tangent at p. course, you're going to say y minus y1 equals the slope times x minus x1. You are going to say that a is x1. You're going to say that y1 is f of a. And of course, you're going to say that the slope of the tangent line is exactly what you gave me, f prime of a. Nothing. I didn't do anything that we haven't used before. This is no news, correct? Okay, so I'm going to write y minus f of a equals f prime of a times x minus a. And all I'm going to do, I'm going to solve like we always do. I'm going to write f prime of a times x minus a plus f of a. We normally write it, I should have put f, this is correct, bless you, but we prefer this in front. We normally don't. In algebra, we normally don't. We want mx plus b, right? But here we're going to write it as f of a plus f prime of a x minus a, and you will see what happens later in Calc 2. So this function approximates f of x near x equals a, which means near a, near point P. So again, what does this mean? I want to go back to the graph for a second. The meaning of all this is the following. Near this point, not near this point, but really, really near this point, it doesn't really matter if I evaluate the function using the function itself or if I evaluate the function using the tangent at P. The error will be very small. Can I approximate here using this? Of course not. Here at this point, I have to find another equation using another slope. Not this slope, but this slope of the tangent. Write the equation of the tangent, and I will say near this point, this is the line, the linear approximation. Here's the line that will approximate at that point. What about here? Can I use any of this? No. I have to draw another tangent. I have to determine another function, and I will say near this point, if I use the function or its tangent, I will get a good approximation. But as you see, it has to be near that point. Okay, one example, and we'll stop after this, I promise. Okay. And this is, by the way, also called a linearization. Okay, we have differential. I'm just going to find the given linear approximation. Okay. Okay, find the linearization. So this is also called L of x. The linearization of f of x near, not at P if you want, but I prefer at near x equals a. Just one example, let's say f of x. This is problem 4 on page 255. F of x is x raised to 3/4 and a equals 16. All I have to do is write L of x equals f of 16 plus f prime of 16 times x minus 16. That will give us the equation of the tangent line at that point, which allows us to estimate the function. Not allows, but it gives us a pretty good estimate of the function if we want to use a linear function instead of this. Do I really want to evaluate this? No. I prefer evaluating a linear function. And if it's not a big difference. If it's a big difference, then I want my function. So I have to find a derivative. So f prime of x, 3/4 x2, 3/4 minus 1, which is negative 1/4, or 3/4, the fourth root of x. So let's find f of 16. F of 16 is 16 raised to 3/4. What I would normally do, yes, you can plug it in the calculator, but you can also replace 16 by 2 to the 4th, and that's so easy. Copy the base, multiply the exponents, and you get 8. Because 4 and 4 will go away, to the third is 8. So this piece is 8. F prime of 16, let's write f prime of 16. Plug in 16. What is the fourth root of 16? The fourth root of 16 is, so 3 divided by 4, this is fourth root of 16. This is 2 times 4 is 8, so 3/8. I have all the pieces, and now I can put everything together to find the function that approximates the original function, the linear function that approximates the original function near 16. Now, if you change this into 20, the function is not good anymore. I have to find another function near 20. So f of 16, we calculated was 8 plus 3/8 times x minus 16. So L of x is 3/8x minus 2 times 3 is 6, and plus 8. So L of x, 3/8x plus 2. This is called the linearization of f of x, which is x to 3/4 near 16. And it's a linear function. So let's say, assuming that this is the function, and let's say that this is 16, and let's say that this f of 16 was 8. If I use the function to evaluate, let's say, at 16.2 or 15.98, I can use this line, which is 3/8x plus 2. Or I can use the function. But this is a very good approximation. If I deviate slightly from 16, using the linear function will give pretty much the same answer. But again, if you move here to 14, you can no longer use that. It's too far away. The error will be big. Any questions?